Hello, in this video I'm going to show you how to build a micro SD card adapter for a 5-volt Arduino. It's very cheap. It'll only take 6 resistors and a voltage regulator, but it does have some limitations in terms of the speed that you can read and write data from the SD card. You'll only be able to use it at SBI half speed, which is about 4 megahertz. To build this project, you're going to need a micro to full-size SD card adapter, some stripboard, an LD1117AV33 voltage regulator or a comparable 3.3 volt voltage regulator, 3 1K8 resistors, 3 3K3 resistors, some header pins, and lastly a short length of wire to cut up and use to bridge between strips on the perf board. I find that single core wire is best for this. This is the circuit diagram that you're aiming to reproduce, and here's the completed adapter. SD cards actually have 9 pins. I've left 8 and 9 off just for clarity here, but that's pin 8. That will be next to pin 7. That's pin 9, which for some reason is all the way up here next to 1. Mainly what's going on here is we have voltage dividers between 10 and 1, 11 and 2, and 13 and 5 to step down the voltage, the 5 volts from the Arduino to 3.3 volts for the SD card. So these voltage dividers are formed of 1K8 resistors directly between the pins that we're joining, and then from the end of the resistor or the pin on the SD card we have 3K3 resistors going to ground. VCC, that would be 5 volts from the Arduino, goes to pin 3 of the voltage regulator. Pin 1's connected to ground, and from pin 2 we have the 3.3 volts going to pin 4 of the SD card, and pins 6 and 3 of the SD card are grounded. That's the whole thing. However, when it comes to wiring up the adapter, you're actually seeing it from the other side. I used the soldering helping hands to hold the 7 straight header pins to pins 1 to 7 of the SD card adapter while I soldered them all in place. While I planned how to lay the circuit out on the strip board, it was useful to label the pins of the SD card with their destinations. First, I fitted all the components in place on the board without soldering them so that I could plan out the best layout. And then I drew that onto squared paper to remind myself where they all went, and also to find out the size of strip board that I would need to cut from the larger piece. These 1K8 resistors form the first half of the 3 voltage dividers on the board. Then these 3K3 resistors form the other halves. They all go down to pin 6, the strip which is connected to pin 6, which will be ground on the completed strip board. This is the voltage regulator, LD117AV33. Pin 1's connected to ground, 5 volt is connected to pin 2, and pin 1 is connected to this rail to the side here. This is where it starts to get a bit more complicated. I've just put in the locations of the jumper wires here. Pin 12 directly to pin 7, because this is the data out. It doesn't need a voltage divider because the Arduino can still detect 3.3 volts as a logic level. Ground goes to that ground rail there, and the 3.3 volt out from the voltage regulator goes to pin 4 on the SD card. So I've just worked out the final size of the piece of strip board that I need to cut out. and I've also drawn that I need to remove the copper from those 4 strips there to divide these. So I've just marked out a 10 by 6 area on the strip board. I'm going to cut down the holes where the red line is. So that's going to form a square this large, which is the same proportion as HD. To make the strip board easier to solder, I rubbed the copper face with fine sandpaper to remove the copper compounds from the surface. Those would have stopped the solder from sticking properly to the copper. Comparing the piece of strip board to my plan, I worked out which 4 squares needed to be removed. Until I watched this video back, I never realised quite how noisy it can get in my studio, where underneath the flight path I have a heliport near us. So now the adapter is ready to test. There's my Arduino Pro Nano. I'm going to plug this in so the first 4 pins match up to pins 10 to 13 on the end of the Arduino. And then I'm going to connect the ground and 5-volt pins of the adapter to VCC and ground on the Arduino. Before I run any test sketches, I plugged the Arduino into the computer via the USB to TTL converter I have, and I tested that pin 4 of the SD card is receiving 3.3 volts. So I'm going to test the adapters I made using the card info sketch from the examples menu. The most important thing to remember when using the SD card library, it seems like a lot of these example sketches have the CS pin set to 4. On this adapter the CS pin is 10. So it made sense to keep it in the standard SPI layout, which I think is consistent across Mini and Nano Arduinos. I have the adapter plugged into the Arduino, as I just showed, except I found out that I had to move the plus 5 volts wire to VCC instead of raw, because raw is only an input. It's for the input voltage, not the output. I have it connected to the computer through this USB to TTL module. Funny enough, when I initially plugged it in, I thought that all of my nice wiring wasn't working. It turned out that this fairly cheap adapter is quite sensitive to how far in the mini SD card is into the adapter. I just played around with that, kind of moving it in or out by different amounts and then running the sketch, Obviously, if you're not so cheap as I was with the SD card adapter, yours will probably work more reliably. But there you go, it's just showing that it can access the card. It's found out the file system type, FAT32, the volume size, etc, etc. So I'm confident that once I start wanting to store files on here, this will all work correctly. Although the card info sketch provided in the Arduino examples did manage to access the card okay, I had some trouble when it came to file reads, writes, etc. And I wonder if that was actually because the formatting of the card was not quite correct for Arduino. However, I found that Google Code archive and downloaded just that first zip file. I think that must be the most recent update to the library, and that actually contains an Arduino card formatter. So once you install that, you'll get SD formatter, and that was actually able to correctly format the SD card to use with the Arduino. Hopefully it will still be compatible with my computer. It formats it to FAT32. Interesting piece of information that the documentation for that library told me is that everywhere all these sketches that I've used have SPI half speed selected as an option. That's because the 8 megahertz full speed SPI will actually set up a kind of resonance in the resistors, and you won't actually be able to use it at full speed. So SPI half speed, which equals about 4 megahertz read speed, is the only one you can use. If you wanted to use full SPI speeds with your SD cards, you could build in an IC based level shifter, or you could just use one of the commercial SD card sockets, but I think it's more interesting to build your own. I'm going to run this sketch read write SD FAT from the library that I just showed the link to, the SD FAT library. That's already uploaded onto the Arduino. So when I open the serial monitor, that will reset the Arduino, and that will cause it to write a file and then read the file contents back. So when I press the reset button on the Arduino, I just got the message, type any character to start. There we go, it's written 1, 2, 3 to the test file and then read it back. In fact, you can see that I've run the sketch twice, because you can see testing 1, 2, 3 twice as the file contents. Here's my obligatory fritzing diagram. This is my adapter here, but I thought it was worth drawing how this would work for a 3.3 volts Arduino, because the SD card functions at 3.3 volts, and the Arduino does too. There would be no need for the resistor level shifters that I included on my adapter, or the voltage regulator. So all the connections could be direct. I mean, this is more like just rerouting of all the pins rather than an adapter. It would still be useful to build this though. So on the 3.3 volt, you'd have pin 10 going directly to pin 1 of the SD card, pin 11 going to pin 2, pin 12 going to pin 7, and pin 13 going to pin 5. And then the rest of these are just power going to pin 4. That would be 3.3 volts coming from the VCC pin of the Arduino, and then ground going to pin 6 and pin 3 of the SD card. So it's kind of worth thinking about this, because this is the actual connection diagram for the SD card. This is what we're trying to achieve in this adapter, except that because pins 1, 2 and pins 1, 2 and 5 of the SD card will be receiving input from the Arduino, we need to shift the 5 volts down using a voltage divider. So from each of these input pins we have a 1K8 resistor going from the Arduino to the card, and then a 3K3 resistor going to ground. The voltage regulator, that's self-explanatory. You connect it to 5 volts in ground, and then you get 3.3 volts which can be supplied to pin 4. Pin 7 can actually be connected directly to the Arduino pin 12, because that's an output from the SD card, and the Arduino can actually accept a 3.3 volt input, so that's all fine. So why bother to go to all this trouble to use a 5 volt Arduino with a 3.3 volts peripheral? The point is that the 5 volt Arduino can run at 16 megahertz, because it needs 5 volts to be stable at 16 megahertz. You can actually overclock an Arduino considerably and still get reasonably stable performance. But if you just want something to work reliably at a high speed, you need to supply it with the correct voltage. And 16 megahertz gives you a lot more flexibility in terms of the speed that you can interface with other devices. For example, 115200 baud serial doesn't really work properly, in my experience, on the 3.3 volt Arduino because the clock speed is just too low. And for instance, I've been trying to interface the OV7670 camera with an Arduino for a while, and that's why I'm actually trying to attach an SD card to the Arduino, because you need very fast. The camera doesn't operate at anything less than 8 megahertz. In fact, it should be 10 megahertz on the if you go by the datasheet for this camera. And you can't really interface a camera whose clock speed is 8 megahertz with an Arduino whose clock speed is 8 megahertz, because each Arduino instruction takes about 2 clock cycles, and you need to run several instructions, well, at least 2, for each data cycle of the camera. However, I've just realized that I may have to go with the proper 3.3 volt to 5 volt level shifter in the end, because the SPI half speed is only 4 megahertz, which in fact won't be fast enough for me to write data to the SD card from the camera. So there you go. If you want just a data logger that will operate over a few weeks, then probably my solution is the one. But if you want to write data fast to an SD card from a camera, you probably need to use one of these. So there you have it, a cheap, simple SD card adapter which will run at half speed, which is probably good for data logging, etc. Of course, if the project you're planning is going to involve a 3.3 volt voltage regulator for any other peripherals as well, you can make this even more economical by just supplying 3.3 volts directly to the adapter board. I hope you liked that video. I hope it was informative, useful. If you're interested in learning more about any other Arduino peripherals, do check out my videos about the generic thermal printer. I also have videos about building a CNC machine using the Arduino based ramps board. So, as ever, if you're interested in open source electronics, CNC machine, Arduino, please do like, subscribe, and have a nice day.